In this lesson, we're going to take a look at a few properties of the definite integral. So first of all, a few definitions. We define the integral from a to a of f of x dx to equal 0. And that makes sense because if you think about what the definite integral from a to a should represent for a function, if we have the graph of a function here, what the left-hand side here should represent would be the area underneath the graph of the curve from x equaling a to x equaling a. Well, what's the area of a straight line segment? Well, that area is 0. Area of a straight line is 0, and so it makes sense that we should define the definite integral from a to be 0. In the second part of our definition, we define the definite integral from b to a of f of x dx to be negative the definite integral from a to b of f of x dx. So in other words, when you flip the order of integration in your definite integral, you introduce a negative. Now, this will make more sense why we define this after we study the next theorem and when we study the fundamental theorem of calculus. Now let's take a look at a theorem. Now in this theorem, we assume that we're given two continuous functions, f and g, and a constant, k. Then we have three parts. The definite integral from a to b of k times f of x dx equals k times the definite integral. So in other words, if k is a constant, you can move the k outside the integral symbol and just evaluate this as k times the definite integral of f. You also have this rule: the definite integral from a to b of f plus g is the definite integral of f plus the definite integral of g. So in a sense, you can distribute the integral symbol to the f and the g. And for our third rule here, the definite integral from a to b of f of x dx is the definite integral from a to c of f plus the definite integral from c to b of f. Now let's take a look at a justification for these three rules, and then we'll look at some examples. So the proof of the first rule is fairly easy. By definition, the definite integral from a to b of k times f of x is the limit as n approaches infinity of our approximating sums k times f of ci times delta x. Remember, the ci is just some point in the ith subinterval. Now, since k is a constant, we can move the k outside the summation, and by rules of limits, remember, since it's a constant that doesn't depend on n, we can move it outside the limit as well, and we end up with this down here. Well, notice then what we have is we just have k times, and this portion right here, is just the definition of our definite integral from a to b of f of x dx. And there we have our result, justifying that you can move the k outside the definite integral. Number 2 is very similar. The definite integral from a to b of f plus g is by definition the limit as n goes to infinity of the summation from 1 to n, f of ci plus g of ci times delta x. This portion right here, remember, that's our approximating sum. You can think of this as being the sum of all of the rectangles that appear under the graph of f plus g. And now notice, we can actually distribute the delta x to the g and the f, and then we can distribute the summation. So what we end up with after we do that is the next line down here. Notice how we distributed the summation to the f and the g, and we distributed the delta x to the f and the g as well. And then we can distribute the word lim, or just distribute the limit to this summation and this summation as well. That's by properties of limits. We end up with this. And by definition, this piece right here is your definite integral of f, and this piece right here is your definite integral of g. And so we've proven our result. For number 3, here's a justification for that. Now down here we have the graph of some arbitrary function. Notice that the area from A to B is this shaded region, and let's just mark with a value right here. Let's put a C value right there. And let's notice then that the definite integral from A to B of f of x dx, well, that's supposed to be the area of this shaded region right in here. And notice if we think of breaking our shaded region up like this, this is equal to the area from A to C, which is represented by our definite integral A to C, plus the area from C to B. And there, we've obtained our result just by looking at it graphically. The integral from A to B of f is the integral from A to C plus the integral from C to B. Now, take note of one other thing. The C doesn't actually have to be between A and B. It can actually be anywhere. For example, if I move C over here, suppose I put C right there. Well, notice then that we have this. The area, I'm going to use shorthand notation here, the area from A to C equals the area from A to B plus the area from B to C. And I'll write that like this, just using some shorthand notation here. A to B plus the area from B to C. Now let's move this, the area from B to C, over to the left-hand side, and we end up with the area from A to C minus the area from B to C equaling the area from A to B. Now, by the rule that we had seen previously, the negative, the definite integral from B to C, is going to be the definite integral from C to B. Remember, this negative forces us to flip those limits of integration, and so we can write this as and there we've obtained the same result that we have over here. The definite integral from A to B equals the definite integral from A to C plus the definite integral from C to B. So it doesn't really matter where that C is. It doesn't have to be between A and B. It can be anywhere. And that's because of that property that we introduced before, that the integral from B to A, we wrote it like this, was negative the integral from A to B. So when you flip your limits of integration, you introduce a negative. Let's take a look at an example. So given that the definite integral of x squared from 1 to 3 is 26 over 3, we saw that in a previous video that we did, evaluate the definite integral from 1 to 3 of 4 times x squared dx. Well, by our theorem, we can just move this 4 outside the definite integral. And we obtain 4 times 26 over 3, or let's see, that's going to be 104 over 3. And if you want a decimal expansion, you can evaluate that on your calculator. Let's look at part 2. So we're given that the definite integral from 1 to 3 of x squared dx is 26 over 3, and the definite integral from 1 to 3 of x cubed is 20. Let's evaluate the definite integral from 1 to 3 of x cubed plus x squared dx. Well, by the theorem we just looked at, we can split this integral apart as we can just distribute our definite integral to both functions, and then this part is 20 plus 26 over 3, and we get and finding a common denominator here, that's going to be 60 plus 26 divided by 3, so 86 over 3. And that concludes our discussion of some basic properties for the definite integral.